Welcome to Alvascience Webinar. Today's presentation will start soon with a short introduction based on a few slides, and will be followed by practical example on how to use our software solutions for model building and validation. At the end of the presentation, we should have time to answer your questions, so please feel free to write your questions in the chat. If you have any suggestion, for example, on topics for future webinars, please send us an email or use the contact form on our site, alvascience.com. This webinar will be recorded and made available on our YouTube channel in the next few days. Without further ado, I'll hand it over to Andrea to start the presentation.
Good morning to everybody. Good morning or good afternoon, depending on where you are. During this webinar, I will show you a brief presentation on the QSAR, QSPR models and how to build them using Alvascience software tools. So I will show you a brief presentation on the QSAR workflow. And then I will show you a few examples on how to use Alvascience software tools in order to build and validate and deploy QSAR, QSPR models. The QSAR, QSPR workflow can be split in 4 different steps: data curation, feature generation, model building and validation, and finally the model deployment. We will briefly have a look at these 4 steps, and then we will see the examples. So what we need before we start, we need a data set of molecules that can be taken from the literature, from online public databases, or from experimental data, or eventually also from internal data that are experimentally taken by your organization or university. So we need a set of molecules, and for every molecule, we need a value for the target variable. The target variable is, for example, a physicochemical property, an ecotoxicological endpoint, the activity, or any variable that we want to model. The target variable can be a quantitative variable if we want to build regression models, or a qualitative variable if we want to build classification models. So once we have collected our data set, we have to curate our data set. What does it mean? It means that typically when we take the data from literature or from online databases, we need to evaluate this data. So we have to check this data in order to see if they are correct, if the structures are correct, if the target is correctly associated to the molecules. We also have to standardize our data set, since typically the data are taken from different sources. And we finally, after the data curation, we need to have a data set without duplicates, with standardized structures, and without structures with possible issues, such as unusual valencies, or for example, if we want to remove some structures that are that we don't want to model, for example, mixtures or inorganic chemicals, and so on. So data curations involves typically different steps. One is the checking of the structures, so that can be used to identify possible issues in our structures, and then the standardization of the structures. So, and these can be used to standardize functional groups. A typical example is the nitro group representation, or also to standardize groups that are not correctly represented in our data set. For example, in this image, we can see an unusual covalent bonds that must be broken. Another task that we need to do during the data curation is the duplicate analysis. That is the identification of possible duplicated structures in our data sets, and the evaluation of these duplicated structures. So the evaluation if those structures have, for example, the same value for the target variable, and then we can, for example, remove all the duplicated structures, or leaving just one of these structure for every group of duplicated structures. And during data curation, we typically want also to analyze our data set. So we can analyze the value of the target variable, but also we can, another typical task that can be performed during data curation is the scaffold analysis. So we can evaluate how many scaffolds are available in our data sets. So how our data set is, how much our data set is represent the chemical space. The next step after the curation, so we have a curated data set, we need to calculate the features. We can calculate the features using Alvascience. Alvascience is our software tool that calculates molecular descriptors and fingerprints. Alvascience calculates almost 6,000 of molecular descriptors and several types of molecular fingerprints. So the input for Alvascience is our chemical data set, SMILES, STF, and so on. Using this data set and Alvascience, we can calculate the molecular descriptors and fingerprints. We can export the features in a text file that can be used by any tool, or we can export the calculated data, so the calculated features and the molecules, as an Alvascience project that is a single file including both the chemical structures and the calculated features. The Alvascience project is the starting point for the model building using our tools. Specifically, is the starting point for the next step, that is the model building and validation that can be performed using AlvaModel. AlvaModel is our software tool that can be used to build regression and classification models, and to validate those models, to apply, to add applicability made to these models, and this is the tool that can be used to deploy the models that we have found. And after the deployment, we can apply our models on a new data set using AlvaRunner. So model building and validation, we will start with an Alvascience project. And to our Alvascience project, we must add the target variable. So we will have one row for every molecule, and for every molecule, we will associate a value for the target variable. Using AlvaModel, we can split our data set in a training and a test set. The training set can be used to build the model, and the test set is an additional set that can be used to externally validate the model. The test set will not be used to build the model, but only to evaluate our model. While during the model building, we can validate our model using an internal validation, that is the cross-validation. The model building is typically the identification of features that are the best features that can be used to model our target variable. Take into account that, as a rule of thumb, the ratio between the number of molecules in your data set and the number of features in your model must be at least greater than 5. So we have to use as few features as possible in order to have a simple model and a model that has not issues related to overfitting, for example. As I said before, the last step is the model deployment. So we have built our models using AlvaModel, and then we want to share our model. We want that other people will use them. And this is typically an overlooked task. There are several papers, including QSAR or QSPR models, also very good models, but not always is the application of these models on new molecules is an easy task. Using Alva model and Alva runner, the application of your models for other researchers is become an easy task. You can share the Alva runner project with your colleagues or with other researchers For example, if you publish a paper, you can provide the Alva runner project as a supplementary material, and anyone having an Alva runner can apply your models on a new data set. Take also into account that Alva runner is free for academic and non-commercial use. So this is our brief presentation. Let's see two examples. In the first example, I will show you how to reproduce an existing model. And in the second example, I will show you how to find a new model, so how to select the best features for a target variable. In the first example, we will reproduce one of the models described by Mansouri and colleagues in the paper called Quantitative Structure-Activity Relationship Models for Ready Biodegradability of Chemicals. The authors provided as supplementary materials the data set, so the SMICE for every molecule, the class of this molecule. This is a classification task, so we have two possible classes. That is RB, that stands for ready biodegradable, and NRB, that stands for not ready biodegradable. Sorry. The authors also provided an additional column, status, that can have two different values, train and test. And this is a variable that can be used to split the data set into training and set and into a training and a test set in the same way as the authors. In this paper, the authors provided three different models, a KNN model, a PLSDA model, and a support vector machine model, plus a consensus model. In this example, we will reproduce the KNN model, but all these models, both the KNN, PLSDA, and support vector machine, and also the consensus model, can be reproduced using Alva model. So, as I said before, the input file that we need to start to build the model is an Alvadesk project. So, we have downloaded the dataset from the supplementary material. We calculated the molecular descriptors for this dataset, and we exported the whole dataset as an Alvadesk project. The dataset includes 1,055 molecules. You can see the dataset as a molecule grid. On the left side of Alva model, you can see a tree view where there are two main nodes, datasets and models. Datasets nodes will collect all the datasets that we will create in our project. We can create multiple datasets. And also under the models node, we will see all the models that we will create in our Alva model project. So we have imported our datasets, so the molecules and the calculated features. Let's also import the target variable. In this case, the target variable is in the same text file that we have downloaded as a supplementary material. So you can see that we have the SMICE, the name, the class, and this additional column that is called status. So let's import the additional variables. Once we have imported them, we can see all these additional variables here. We can define which columns we want to see in this data grid. We can also sort or filter the data sets using all these columns. So now we have one single data set, that is the master. We want to split our data set into training and test set. So let's go to dataset split training test menu. Alva model provides different type of splitting for that we can use in order to split our dataset into training and test. We need to choose our source dataset. In this case, we have only one dataset that is master. We can define the name of the two datasets that we will create. We can define some options, for example, the size of the training set, the percentage of molecules that we will assign to the training set, and the type of splitting, Venetian blinds, contiguous block, and random splitting. But anyway, in this case, we want to split the dataset in the same way as the authors did. So we can select the status column, and we will tell to Alva model that the molecules having a value equal to train for the column status will be assigned to the training set. All the other molecules will be assigned to the test set. So just click OK, and we can see in the datasets preview that under the datasets node, two additional datasets, training and test. Training has 837 molecules. We can see it in the status bar that will tell us how many molecules we can see in our grid. And in the test set, we have 218 molecules. So we have split our data set, and now we can prepare our model. So I have said, as I said before, we want to reproduce an existing model. Our model provides two different types of model building. This add model that can be used when you already know which variable you want to use in your models, or the automatic models generation that can be used when you don't know exactly which variables you want to include in our model, in your model. So using the automatic models generation, Alva model will look for the best features that can be used to predict your target variable. The automatic model generation uses genetic algorithms to identify the best features. We will see how to use the automatic models generation feature in the next example. So let's add a model. This is a step-by-step procedure. The step-by-step procedure under add model and under automatic model generation is quite the same, just one step is different. We will see then. During the first step, we have to choose if we want to build a regression or a classification model. In this case, we want to build a classification model. We can choose which type of model we want to implement: linear discriminant analysis, quadratic discriminant analysis, PLSDA, and so on. In this case, we want to build a KNN model. The authors defined k equal to 6, but let's try with a k equal to 5. That is the default proposed by Alva model, and we will see later how to change this value. They use the Euclidean distance in this KNN model. So let's go to the next step. The next step, we have to choose between the training set and the test set. The test set is not mandatory, but as we want to reproduce exactly the model described by the authors, we will use the same training and test set used by Mansouri and colleagues. In the next step, we need to choose the target variable. In this case, the target variable is named class, and we will choose as positive class the ready biodegradable class, as the authors did, and then we have to select the descriptors proposed by the authors. As you can see here, we calculated more than 4,000 descriptors for this data set. The KNN model, if I remember, includes 12 descriptors. So we have to select these descriptors manually. We can use the filter options. For example, one of the descriptors is the number of oxygen atoms. Anyway, since there are 12 descriptors, I don't remember exactly those descriptors. I already prepared a template file. A template file is a file including a specific selection of descriptors. So in this case, I prepared the template file for the KNN ready biodegradability model. It includes, as you can see, 12 descriptors. In the constitutional descriptors, 3 descriptors are selected. The number of oxygen atoms, I remembered well, the number of heavy atoms, and the percentage of carbon atoms, for example. So we have selected the descriptors for our model, and we can go to the next step. But before, we have to select the pretreatment of the features. The features can be used as they are, so if we don't want to scale the features, we will let this option to none. But in this case, we want to standardize the features like the authors. And typically this is useful if you don't use, for example, a distance type that take into account the variance of the features. Otherwise, features that take high values can be more important in the model than descriptors that have a lower value. So in this case, we use the pretreatment, the standardization. So all the features will be standardized with an average equal to 0 and standard deviation equal to 1. In the last step, we can choose some options to reduce the number of features. We don't need to do this in this case, since we have already selected 12 descriptors, the 12 descriptors that we want. And but this can be useful if we have selected a lot of descriptors, for example, a whole descriptor block. Since, as I said before, the ratio between the number of samples and the number of features must always be at least equal to 5. So let's press finish, and here we have our first model that is named class KNN1. And here we can see our model. Specifically, there are 3 sections. The model detail, where we can see the information about our model, so the name, the model type, the target variable, the type of pretreatment, the included features. We can also see the percentage of the ready biodegradability, so the positive class, the substances with the value RB, that is less than 34%, and the number of molecules belonging to the negative class. And also we can see the number of molecules belonging to the training set and the scores calculated for this model, so the sensitivity, the specificity, the accuracy, and the balanced accuracy that are calculated by default. We can also change the information that we can see. In this case, we are looking at the information for the training set, but we can also have a look at the information about the test set, so we can see the sensitivity, specificity, accuracy, and balanced accuracy for the test set, and also the distribution of the positive and negative class in the test set. And we can also see the information about the whole dataset. Take into account that if we switch between these 3 dataset representation, the confusion matrix on the right side and the molecular dataset on the bottom side will be updated accordingly. And for example, if we select the whole dataset, so both the training and the test set, we can see in the model detail the information about the training and the test set. So the scores calculated both on the training and the test set. We can see the confusion matrix calculated on both the training and the test set, and we can see in the grid below the whole dataset, both the training and the test. And the test set is highlighted in light blue, and the training set is highlighted in light green. In this molecule grid, we can see the molecules, the target variable, in this case class, the predicted value for that are predicted by this model, and an additional column called correct that can have 2 different values. 1 if the prediction is correct, 0 if the prediction is not correct, and the features that are used by our model. So in this case, we can sort and filter our data set. For example, we can filter our data set in order to see the wrongly predicted molecules. For example, we can see that we have these molecules that are 156 molecules that are wrongly predicted. So let's clear our filters for a moment, and we will see how we can change the K value for the model, since we have seen that the model described by the authors uses a K equal to 6, while actually we are using a K equal to 5. And we have seen that we have 157 molecules that are wrongly predicted. So let's go in the main, in the tree view under the models. So we can right click on our model and we can select this option, that is optimize K. Using this option, we can change the K value for a KNN model. So our model will look for all the scores, will calculate all the scores, iterating using a K equal to 2 until a K equal to 20. And so we will see all these scores calculated from K 2 to 20. And we can copy the results, or we can also sort this grid. And sorting this grid, we can see that the best model, so the model with the best accuracy, is the model having K equal to 6. So we can select this model. In this case, we are on this row. We can just click OK. So we will change the value of K for our model from 5 to 6. The model is recalibrated, and now we can see if the model, how the model has been improved. So now we can see that the number of wrongly predicted samples decreases, since we from 157 to 140. Where we are in the confusion matrix panel, we can also see some charts. For example, we can see the distribution of the chart of the value of our features in the data set. In this case, you can see in green the not selected, not filtered molecules that are not filtered by the molecule grid. So we can see that the wrongly predicted molecules belongs to these bins. We can clear all filters. So we can see the distribution of the number of oxygen atoms in our data set, both in the training in green and in the test set in blue. So we have seen how to optimize our K. We can also add additional scores to our model. For example, we can add the cross-validated scores, sensitivity, accuracy, specificity, and balanced accuracy. Once we calculated those additional scores, they are automatically added to the model detail. So we can see also the cross-validated scores for the training set. An additional feature that I want to show you is the possibility to add the applicability domain. You can choose between different types of applicability domain, different types of applicability domain. One is based on leverage and one is based on distance. You can choose different type of distances and a different type of approach. So in this case, we have used for the model the Euclidean distance. So let's select the average distance and let the default value for the threshold factor. If we click OK, another tab is added in molecule detail, and we can see that the applicability domain is added. This is the description of the applicability domain. We can see how many molecules in the training set belongs to the applicability domain and how many molecules for the test set belongs to the applicability domain. We can add a different applicability domain to our model, and then we can select the preferred applicability domain. We can also export the results as a tabulated text file, so the information about the molecules, the prediction, the target variable, and the calculated features. But we can also export the models. when we export the model, when we export our models, we do this in order to deploy our model and share our models with other researchers. So exporting the models is a step that is needed to create an Alvarunner project that can be shared and used by others. So we can define a name. For example, this is RBV version 01. We can add a description for our model, and we can select one or more models that we want to export. So just click OK and save our model as an Alvarunner project. At the end of this presentation, I will show you how an Alvarunner project can be used to apply the models on a new dataset. So we have seen how we can reproduce an existing model. And now let's see how we can find new models starting from a dataset and a dataset with molecular descriptors. So in this next example, we will import another Alvascience project. So a dataset including molecules and descriptors. This dataset has been taken from the literature too. This dataset has been presented by Grisoni and colleagues in the paper whose title is Acceptable by Design QSARs to Predict the Dietary Biomagnification of Organic Chemicals in Fish. In this paper, the authors presented two different models, regression models, one KNN model and one ordinary least squares regression model, plus a consensus model. But in this case, we don't want to, I will not show you how to reproduce this model, but how to find new models in our, for our target variable. Target variable is the biomagnification factor. So we have imported our Alvascience project. These are two, in this case, the dataset is smaller, so we have only 214 molecules. Let's import the target variable. The target variable is the log BMF, and we will have an additional column that is called train, that brings the same information as before. So before we have a column called status, if I will remember, with two different values, train and test. In this case, we have a column called train with two different values, 0 and 1. Let's import the target variable. Once we have imported our target variable, we can go further. Since, as I said before, we always need a dataset of molecules and a target variable. So the endpoint that we want to model. So let's split our dataset into a training and a test set. So let's select the column train. And for the training value, the value used by the authors is 1. If I will remember, eventually we will change it. So the dataset has been splitted. We have two additional datasets, the training and the test set, as we have seen before. In the training set, we have 160 molecules, and we have 54 molecules in the test set. So now we don't want to add a model that is already known, so we don't want to reproduce an existing model, but we want to find a new model. So let's do the automatic models generation. The step-by-step procedure is quite the same as for the model generation. So we have to select if we want a regression model, build a regression or a classification model, in this case, a regression model. This is the additional step that is not, you don't have to do if you already know the variable that you want to include in your model. During this step, you can set some parameters for the genetic algorithms, and you have to set the score, the type of score that you want to optimize. So just a few words, the genetic algorithms do not identify one single model, but a population of models. So you need to set the number of models that will be included in your population, so the population size. Anyway, we will let these options, this parameter as by default. We can define the maximum number of iterations, the maximum number of features that we want to include in our model. If I well remember, for this data set, the authors provided one ordinary least square regression model using 7 variables. Anyway, let's. This is just an example, so we can use just 5. We have to define the score that we want to optimize. In this case, we want to optimize a cross-validated score, since R square is a fitting score, while the cross-validated scores are RMC, the root mean square error, and fold, and Q square and fold. There is also the possibility to optimize the Q square, leave one out for very small data sets. So we will optimize the Q square and fold with 5 folds. We can select different type of models, also in this case for regression, linear regression, partial least squares, KNN, support vector machine, and in this case we will just try with the support vector machine, since this is not a model that is already included in the paper. So let's select support vector machine and model type, and then select the training and the test set. As before, we can leave the training set and the test set as the authors did. The target variable is the log BMF, and then we have to select the descriptors that we want to use for the identification of the molecular features. If we already know that some descriptors are not useful, we can exclude this descriptor block. In this case, we just select all the descriptors, so more than 4,000 of descriptors. Also in this case, we can standardize the molecular features, and then we go to the last step, that is the variable reduction. We can go further without removing any variable, so without doing any variable reduction. But in this case, let's try with the per correlation variable reduction. These variable reduction techniques excludes all the one for every pair of features that have a correlation higher than the threshold. So after this variable reduction, we will not have in our data set descriptors, pair of descriptors with a correlation, an absolute correlation larger than 0.95. So let's start. You can see the progress, the trend, the progress of the genetic algorithms, and the trend of the score, and the number of iteration. So in this case, you can see the maximum value, the best score individuated since now for the Q square and fold, and the best model that is identified. Typically, I suggest to run several genetic algorithms, several runs for genetic algorithms. So this is one run. I will identify some models, and then I will run these genetic algorithms again, since the descriptor space is very, very big, and it's quite easy to identify a local optimum. So in order to explore in the better way, in the best way, all the chemicals, all the descriptor space, I suggest always to do more than one run. Anyway, we can pause our genetic algorithms, and we can evaluate the models identified until now, and we can also select some of them that we think that are good models. For example, we can save this model, and for example, I don't know, this one. I'm just saving 2 models since I want to show you how to build the consensus model. So we can restart the genetic algorithms and we can have a look at our models. So when we select, you can see that under models, we currently see the two models that we have saved and the automatic models generation. So we can see how the genetic algorithms are going, and we can also evaluate our models. Also, in this case, we can see the information about the whole data set, the training set, or the test set. We can see the information, the scores about our the whole data set, so the Q-square on the training set and the R-square on the test set. We can evaluate the charts. We can explore the charts evaluating the molecules. We can see the scatter plot. We can see the residuals, and we can see also the distribution of the features values in our data sets. We can also have a look at the Williams plot that can be used to identify possible outliers. Just to show you, if we select a set of molecules in the chart, they are automatically selected in the grid below. So we can see that those molecules that are probably outside the applicability domain for this model are these 8 molecules. So we can copy the charts, save the data associated with the charts, and so on. So let's go again to the scatter plot. Let's pause. As you can see, the scores is continuously increasing, so the genetic algorithms are doing their job. So let's pause and stop. So we will discard these models. We have already saved the 2 models we are interested in. We can see under this node the information about all the models we have saved until now. And now have a look on how to build a consensus model. So let's go to Models menu, Add Model. We want to add a regression model, and in this case, we want to build a consensus model. In order to build a consensus model, we just have to select the models, at least 2 models, that we want to use for our consensus model. So this is our consensus model. Typically, consensus models have better scores than single models, okay, but in this case, we are not evaluating good models. Okay, they are quite good, but okay, there are a lot of molecules that must be investigated. So this is just how we can identify new models using the automatic model generation and how we can build a consensus model. Just other few things about Alva model, and then we will go to AlvaRunner. So we will see how we can apply models that we have developed using Alva model on a new data set. We can add this new scores, as we have seen before for the classification models, and we can also evaluate the performance of the models using wide randomization. So that is a technique that can be used to identify the possibility of chance correlation. We can also add the applicability domain, and as before, we can add a different type of applicability domain, and we can add a different applicability domain to a single model, and we can select the applicability domain that we prefer. We can, in the same way as before, export our models. In this case, you can see that we have 3 models. We can export all the 3 models as an AlvaRunner project. And once we have exported the model, we can share this AlvaRunner project with other researchers that will apply these models on their data set. And so let's have a look on how we can do this. So let's open AlvaRunner. AlvaRunner does, in order to apply your models on a new data set, does not need any other tools. You just need to open your model, open your Alvarunner project. In this case, let's have a look at the biomagnification factor models. This Alvarunner project is available on our website, so you can download and test it. And it includes the free models proposed by Grisoni and colleagues for the biomagnification factor. So we can see, once we have opened our Alvarunner project, that it includes free models, a KNN model, and we can see the scores for the models. For this model, we can see the detail for the model, so the variable that are included in this model, if there is a pretreatment, which type of pretreatment, the number of molecules in the training set, if there is an applicability domain, and which type of applicability domain. You can see the detail for every model. This is a consensus model and the performances of this consensus model. We can also save the training set as a SMICE file or SMICE files with header. And once we have imported our model, we can just open or drag a molecule file on Alvarunner. In this case, we can use not this because BMF is the original training set. We don't want to use it. So this is a SMICE file. We just need to open the SMICE file, and all the descriptors are calculated, and all the models are applied to our data set. We can filter and sort our data set, and we can see that we have free models. All the free models have an applicability domain. So the first one is a KNN model. The applicability domain for this model is a distance-based applicability domain. The second model is an ordinary least squares regression model, and the applicability domain is based on leverage. And finally, we have a consensus model, where the applicability domain for the consensus model is considered, the prediction is considered inside the applicability domain if all the models included in the consensus are have the prediction inside the applicability domain. If just one of the model, if for just one of the models the molecule is considered outside the applicability domain, also the consensus model will consider the prediction outside the applicability domain. I forgot to show you one thing in Alva model, that is the prediction detail, but I can show you now, since the prediction detail is a feature that is available both for Alva model and Alvarunner. The prediction detail provides us some information about how the prediction have been performed. For example, in Alvarunner, we just double-click on the cell corresponding to a molecule and the model to see the prediction detail. What is the prediction detail? This is the prediction detail. This is our target molecule. This is the predicted value for our target molecule. This is the applicability domain information, that is 1 if the molecule is inside the applicability domain, and 0 if the molecule is outside the applicability domain. So this molecule is considered inside the applicability domain. We have the neighbors that have been used to predict the log BMF value for this molecule. We have these 7 neighbors. And here we can see the atomic and the fragment contributions. What does it mean? That we can see the atoms and the fragments of the molecules are highlighted in red or in blue. They are highlighted in red if the contribution of the atoms or the contribution of the fragment is positive, and in blue if the contribution of the atom or the contribution of the fragment. In the fragment are the side chains or the framework. So we can see in red the positive contributions, and in blue the negative contributions to the prediction. Okay, so this can help us in order to better understand how the model is working on our molecules, on our data set. This feature is available also in Alva model. Maybe I already opened. Okay, here Alva model. We can, for example, click on one of these molecules in order to see the prediction detail also in Alva model. Taking into account that we can see the neighbors if we have a KNN model. Otherwise, we don't. The prediction detail will not show us the information about the neighbors since they are not used for the prediction. One last thing. Alva Runner is provided both with a graphical interface. It's available for Windows, Linux, and Mac, and is provided also with a command line interface that can be useful if you want to integrate the application of the QSAR or QSPR model in your workflow. And we also provide the extension for KNIME, so Alva Runner can be easily integrated in KNIME too. I hope that I've said everything that's important. Okay, there are a lot of features, there are a lot of things that I didn't say during this webinar, but I hope that I say something that could be interesting for you. So
thank you, Andrea.
Thank you, Matteo.
I wanted to mention a couple of things since I follow the chat and try to reply to a few questions. Basically, this is it's not the last webinar, so we will have other webinars like this one. So if you want to get in touch with us and suggest topics or things you are interested in for future webinars, please do so either through email or using our contact form on Alvascience website, which is alvascience.com. I wanted also to mention, since this has been asked several times, that the recording of this webinar will be available on our YouTube channel in the following few days. Again, you can find a link to our YouTube channel on our site. And if you are interested in our software solutions or you want to try them, you can get in touch, as mentioned before. Since we don't have much time left, Andrea, I wanted to ask you a couple of things that were revolving around chemical data curation. So basically, someone specifically asked about what software to use about chemical data curation, and I'll connect another question with which was mentioned at the beginning, which was related to the duplicate feature and how to handle duplicates, since I know it's a feature that will be soon released.
Okay, Alva Molecule can be used for data curation. Currently, Alva Molecule does not include the possibility to identify duplicates, but we are releasing Alva Molecule 2.0 that will probably be released in the second half of 2022, sorry. And it will include both the duplicate analysis and the scaffold analysis. So stay tuned. So since the new version of Alva Molecule will include a lot of very, very interesting features.
Okay, one last thing. I don't think there is an exact answer to this one, but it was what is the minimum number of descriptor for a model? And since you refer also to sort of rule of thumb about the maximum number of descriptors, I wanted to ask you this.
There is, okay, the minimum number of descriptors per model is 1. Since, for example, some descriptors are complex descriptors. So we can consider as a descriptors also the log P. There are in Alvascience calculates, for example, 3 different log P models plus a consensus model for log P. This can be considered as a descriptor, but it's also a single descriptor that can be used to predict the log P. So it depends. Anyway, I don't really know models with less than 2 descriptors. But anyway, typically between, and also depends on which type of descriptors, how much are you interested in the interpretation of the model, or if you are only interested in the performances. So if you want to specifically identify and understand how your model works, less descriptors you have, easier is the interpretation of your model. There are models that are more interpretable, models that are more difficult to be interpreted, and this is one of the reasons that why we added the prediction detail. So we are going in the direction that will help the users in order to understand how the model is working. But okay, okay, 2, 1, 2. No, there is no minimum descriptors. Minimum descriptors.
Okay. I think we should do maybe a webinar all on the following questions, which is how the atomic and fragment contributions to the prediction are actually calculated.
Okay.
It's not an easy question.
No, we take inspiration on 2 papers, one from Rineker and Landrum for the atomic contributions, and for the fragment contribution from Polichuk and colleagues. Anyway, if you want to test, or if you are already using Alva Runner and Alva model, you can just have a look at the help provided with the software. So we can see, for example, this is the help for Alva model, and you can see work with the model. At the end, you can find the information about the project, the prediction detail, and how it works, and also the references. So this is quite detailed help. So you can find the information about how it works, so how it calculates the atomic and fragment contributions, and you can also check the original papers where these approaches are described. So you can see this one. This is for the atomic contribution, and this is for the fragment contribution. So the prediction detail is inspired by these 2 papers.
Okay, I think this is all we have to give for today. So I hope you enjoyed, and see you at the next event.
So thank you for your attention, and see you soon.
Have a nice day. Bye-bye.
Bye.